Hi, hello, welcome. This is Discrete Mathematics, and today we are continuing Section 1.1, Sets and Logic. We're starting here with Venn diagrams. In our last video, we looked at ways to express sets using set notation and things like subsets and is an element or not. Today we are going to look at a visual way to represent sets, and that is with the Venn diagram. So Venn diagrams are good for visualize sets or relationships between sets. First up, we want to look at a Venn diagram of A is a subset of B. So here is my universe, and here is B, and then A is a subset of B, means A is entirely inside of B. Every element of A is also an element of B. There's no elements of A that are outside of B. A is a subset of B. Next up is A union B. So here we'll draw A and B, and this is our universe, and A or B, or A union B, is everything that's in A or B, or both. So we have that region shaded. Next up is A intersect B, A and B. Here's A, here's B, and this, of course, is our universe. A intersect B is the things that are in both sets. So that's this region in the middle that they share. Next one is A minus B. Here is, oops, I made a square. I kind of wanted a rectangle. There we go. Here's A and B. And this is our universe. A minus B is everything that's in A except for the things that are also in B. So just this part. So it's almost like we took all of A but took off this intersected piece. Everything that's in A that's not in B. Last up is A complement, written with the bar across or with the C, and that is the whole universe minus A. Here is my universe. Here is A. So A complement would be everything that's in the universe that's not in A. It's the opposite of A, all that stuff. Venn diagrams are a good way to visualize relationships between two sets, especially when things get a little bit complicated, like we're going to see here in example 7. Example 7 is kind of like a logic puzzle. So if you find yourself enjoying logic puzzles, maybe you'll enjoy this one. But we're going to solve this problem by drawing a big Venn diagram. There's our universe. Here we have 1 circle, 2 circles, and 3 circles. So this first circle, we're going to let that one be calculus. This is our universe. This one is going to be computer science. And this one is going to be psychology. All right, and we're just going to go through all of the things it's telling us and write it in our Venn diagram. So first up, it's telling us that 8 students are taking calculus, psychology, and computer science. So that's all of them. This is the region where we see all of them intersecting. So that's the 8 students are taking calculus, psychology, and computer science. Next up, we see that 33 are taking calculus and computer science. So this piece right here is calculus and computer science. And we know that there are 33 in this piece, but 8 of them are here. So whatever's left over is in here. So this is going to be our 33 minus 8, which is 25. So 25 students are here, 8 are here. Together, that's our 33. Next up, 20 students are taking calculus and psychology. Calculus and psychology, that's this section. So we're going to do something similar. 20 minus 8, which is in the middle section, is 12. So we're going to keep doing this all the way around. 24 are taking psychology and computer science. Let's see, I'll pick another color. So this one is 24 minus 8, which is 16. All right, next up, 79 are taking calculus. This is where it's going to start to get interesting. Maybe I'll do a darker blue. So for our calculus piece, that's this whole thing, and that's 79. But I already have some of the numbers in there. So that's minus 12, minus 25, and minus 8. So how much is left? That's 34. And we're going to do that for all of these outer rings. Next up is computer science. Next up is psychology. We will do like a light green. This one is psychology. That is 83 minus 12 minus 8 minus 16. And that is going to be 47. And then last one is computer science. That's this one right here. So for computer science, we've got 63 minus 25 minus 8 minus 16, which is 14. So now we have every individual piece of our Venn diagram except for what's outside of everything. And that's what we're supposed to find in part A. How many students are taking none of the 3 courses? So we need to figure out what are all of these numbers added together. And I'm going to subtract that from 165, which is the total number of students. So I know I could add all 4 of these together. That's the number of students taking calculus. That's 79. So that's all of these. Next up, I'm going to do the 47, 16, and 14. And that all together is 9. So there are 9 students that are not taking any of the 3 courses. And in part B, I want to know how many students are taking calculus or psychology. So that would be calculus or psychology. Are these 2, or just calculus, or just psychology. So calculus or psychology is all 3 of these pieces added together, in calculus or psychology or both. So I'm going to add up all those. Again, I know how many students are taking calculus. That's the 79. And then I want to add the 47 and the 16. And that all together is 142 are taking calculus or psychology. So in this problem, we were able to use a Venn diagram to help us figure out this really complicated situation. We could have done this all using set notation, but I think it maybe would have been a little bit more complicated than having this visualization. All right, let's talk about some laws. Here are set laws. This is from your textbook, Theorem 1.1.22. First up, we have the commutative law, and this says that A intersect B is the same as B intersect A. So if you have A and B, their intersection is this way. It doesn't matter if A is on the left and B is on the right, or if it's the other way. Let's say this is B and this is A. The piece that we want is still that middle piece, regardless of which way you do it. And similar with the union, A union B and B union A are the same. Next up is associative laws. The associative law says if I have A intersect B intersect C, it doesn't matter if I put the parentheses over here or over here. It doesn't matter which one I do first. So if I draw a small picture, let's say I have A and B and C. A intersect B intersect C is going to be this middle piece right in here. And so it doesn't matter which order I do things in, I'm still going to end up with just that one middle piece, regardless of whether I do B intersect C first or A intersect B first. And similarly with the union, A union B union C is going to be all of this. And it doesn't matter which part I union first. Distributive law. I have so the difference between associative and distributive is in this associative law, all of my symbols were the same. I have A intersect B intersect C, and A intersect B intersect C. And then this second one, I had all unions. So in this distributive law, I've got a mix of intersections and unions, and how am I going to deal with that? So we can think of it like distributing. Like if I had 3 times x plus 5, I would distribute this 3, and I would have 3 times x plus 3 times x plus 3 times 5. So that's what I'm going to do here. I'm going to take A intersect the quantity B union C, and I'm going to have A intersect B union A intersect C. So I'm distributing this A and the intersect to both of the things inside the parentheses, and then I'm keeping this symbol that was in the parentheses, much like I did up here. We can look at this with the Venn diagram. So maybe I'll show this one down here. I've got some room. Here is A and B and C. Oh, I didn't make them nice this time. Let's see. I want A intersect B union C. So we'll do B union C first because that's in parentheses. That's this whole thing, all of B and all of C and all of their intersection. And then I want where A is united with that. Or sorry, I'm intersecting A with that. So that's this green area right here is A intersect B union C. So let's look at the right-hand side and see if that's the same thing. Here's A and B and C. A intersect B is this part, and A intersect C is this part, and so their union is this whole part, like that. And I can see that this area that I've done in green is the same on both sides. So this works if I am intersecting into the parentheses. That's the one I just showed. It also works if I'm going the other way. If I'm doing A union B intersect C, I would distribute the A and the union to the B, and the A and the union to the C, and then I still have this intersect in there from before. So that is the distributive law. The next law is the identity law, and that says that A union with the empty set is just A, because there's no elements in the empty set. So you can add that. It's like adding 0. It's not going to change whatever number you're dealing with. And then I can also look at A intersect with the universe. And so that's everything that A and the universe have in common, which is just A. The complement law says that A union A complement is the universe. And we could go back and look at when I defined A complement. That was everything that's not in A. So if I unite that with everything that is in A, I'm left with everything. And similarly, A intersect A complement is the empty set, because A complement is everything that's not in A. So it doesn't have anything in common with A because it's everything except A. So intersect that with A and you have nothing. Idempotent law, A union A is A. If you combine A with itself, you just get A. And A intersect A is also A. So this is kind of like an identity. If you unite A with itself, you get A. If you intersect A with itself, you just get A. Bound laws, that's what we're talking about next, is A intersect the empty set is the empty set. There's nothing in the empty set, so whatever you intersect that with is going to be nothing. And if anything that unite with the universe is going to be the universe, because the universe is everything. So add anything to the universe, whatever you're adding is already in the universe. So you're left with the universe. Absorption laws, A union B intersect A intersect B is A. So you're uniting A with A intersect B. A intersect B is everything that's in A and B. And then, so everything that's in this green part is also in A. So if you unite that with A, you're going to be left with A. And if you do A union B intersect with A, you'll again just have A. Involution law, the double complement, A complement complement is A. So A complement is everything that's not in A, and then the complement of that, you're back to just A. The 0-1 law, the complement of the empty set is the universe, and the complement of the universe is the empty set. And last one is we have a De Morgan's law for sets. And that is saying that A union B, that whole thing complement, is A complement intersect B complement. So let's maybe take a closer look at this one. Here I'm going to draw a picture. Here's A and here's B. And I'm looking at A union B complement. So A union B is everything that's inside these circles. So the complement would be everything else. So this is A union B complement, everything else. Let's take a look at A complement intersect B complement. Here's A and here's B. So A complement is going to be all of this. And B complement is going to be all of this. And so I want that intersection. Where is green and purple both shaded? I'm going to add a new color, yellow, and that's out here, which is the same as the area that's not in A or B, which is the same as I saw over here. So that's De Morgan's laws. One way you can think about De Morgan's laws is you can think about giving this complement to everything inside the parentheses. So A union B complement can be A complement and then union complement and then B complement. And just to note that this union complement isn't really a symbol that exists. So what you do instead is you change it to the other symbol, which is an intersection. So this is A complement intersect B complement. This is a way that you can think about how this is going to work algebraically, I guess. So we could apply this idea to another example. What if I had A intersect B complement and I wanted that complement? So that would be A complement. And then if I complement this intersection, it turns into a union. And then B complement complement is actually just going to be B. So this would be A complement union B. So you can use this algebra idea to extend De Morgan's laws to more complicated situations like this one that I did down here in orange. Okay, next up is extending the ideas of intersection and union to multiple elements. So if I have a collection of sets where S is the set that contains A1, A2, A3, all the way up to AN, where each of those is a set, and I wanted to find the intersection of S, I can look at the intersection of each of those individual sets. And I can do the same thing with the union. So I can extend this idea. So far I've looked at 2, maybe 3 sets. I can extend this idea to sets within sets, to more than just 2 or 3 sets, using these larger symbols, intersection and union. Notice that these larger symbols, where we're adding up multiple sets, look very similar to the ones that we have used to look at just between 2 sets. Okay, next up, sets X and Y are disjoint if X intersect Y is the empty set. Disjoint, so they don't have anything in common. So if I'm looking at a picture, here's A, here's B, their intersection is empty. So there's no overlapping anywhere. A and B are completely separate sets. Those 2 sets are considered disjoint. A collection of sets, so I can extend this to more than 2 sets, is pairwise disjoint if you take any combination of those sets and they're all disjoint. So every pair is disjoint. So if they were all circles within our universe, none of the circles would be overlapping with any of the other circles. They would all be totally separate circles. That's pairwise disjoint. Every pair is disjoint. However many pairs you can make, they're all separate. This brings us to the idea of a partition. If X is a non-empty set, then a partition of X is a set of disjoint sets whose union is X. If X is a non-empty set, then S is a partition if every element of X belongs to exactly one element of S. So let's take a look at an example here in example 8. let X equal the set 1, 2, 3, 4, 5, 6, 7, and 8. Then let S be the set that contains the set of 1, set 2, 3, and 4, set 5 and 6, set 7, and set 8. So now we can see that S is a partition of X. Because if you would unite all of the sets within X, we would come up with S. Or unite all of the sets within S, we would arrive back at X. Every element that's in X is in one of the sets within S. So it's kind of like we're carving up this set X into 1, 2, 3, 4, 5, and 6, and then 7 and 8. And as you see, I'm doing this, there are multiple ways to cut up set X. I've chosen a way where S, the cardinality of S, is 5. But I could do another partition, let's call it T. Ooh, that's not a very good T. Where T is the set of the set 1, 2, 3, and then maybe we'll do 4, 5, 6. Oh, let's just do the rest. 7, 8, 6, 7, and 8. So T is also a partition of X. The cardinality of T is 2, because I've got this set, the set that contains 1, 2, 3, and then the second one, which is all the rest. So I've broken S up into two different sets. So T is a partition, the cardinality of T is 2. So this is the idea of a partition. Okay, last topic for this section is called the Cartesian product. The Cartesian product of sets A and B is the set of all distinct ordered pairs where A is in set A and B is an element of set B. So just a note, we've been talking about these curly braces, set notation. We've been using that a lot. A and B is equal to BA. These are both sets. And in sets, we don't really care about the order. The order of a set doesn't matter. We usually write it in alphabetical order or numerical order. That's just easier to keep track of, but there's no difference between these two sets. Right now, in Cartesian products, we're talking about ordered pairs. So an ordered pair is parentheses. So AB is not the same as BA. Those are two different things. In an ordered pair, the order matters. Ordered is in the name. So these Cartesian products that we're going to look at are sets that contain ordered pairs. We're going to do example 9. Let X be the set C, D, and F, and Y be the set 3, 9. We want to find X cross Y, so the Cartesian product of X and Y cross X, X cross X, Y cross Y, and I want to find the cardinality of each one. Let's start with X cross Y. So that's going to be a set that contains a bunch of ordered pairs. And in my ordered pairs, the first element of my ordered pair is going to be something from X, C, D, or F, and the second is going to be something from Y. And I want to do all possible pairs. So I'm going to start off with C, 3. And then the next one is going to be C, 9. And the next one, I've already done C, so now I'm ready for D, 3. And then D9. And then F3, a lot of commas. And then F9. And I think that's all the possible combinations. The cardinality of X cross Y is 1, 2, 3, 4, 5, 6. 6. And it's actually the same thing as the cardinality of X times the cardinality of Y, because we're taking every element from X and combining it with Y. So how many combinations are there? That's 3 times 2, which is 6. So multiple ways to think about this. Let's try Y cross X and see if that's the same as X cross Y. If you're looking below, you're thinking that it's not the same. So in Y cross X, I want all the ordered pairs, but this time the first element has to be something from Y. That's the 3 or the 9. And the second element is something from X. So we'll start with 3C, and then 3D, and then 3F. And now we're ready to move on to 9, 9C, 9D, and 9F. And I think that's it. The cardinality of y cross x is the cardinality of y times the cardinality of x, which is 2 times 3, which is also 6. So even though x cross y and y cross x have different elements, they have the same cardinality. And I have that note down here. A cross B is not the same as B cross A. If A and B were the same, then they would be the same. But if A and B are different, then we're looking at the cardinalities are the same, but the actual elements in the sets, the ordered pairs within the sets are different. They actually are very similar. Like we can find, here's C3 and here's 3C. But this order matters. Here's C9 and here's 9C. So we'll see all of the same like numbers and letters, but the order is switched. And since it's an ordered pair, the order matters. So these are not the same. Let's do x cross x. And that is going to be first element from x, second element also from x. So we'll have C with C, and then C with D, and then C with F. And then D with C, which is different than CD. And then D with itself, and then D with F, and then F with C, F with D, and F with itself. This one looks like it has more elements. X cross x, the cardinality of that is the cardinality of x times the cardinality of x, which is 3 times 3. So now here we have 9 elements in this set. Last one is y cross y. Y cross y is going to be 3, 3, 3, 9, 9, 3, and 9, 9. This one is shorter because y only has 2 elements. So the cardinality of y cross y is the cardinality of y times the cardinality of y, 2 times 2, which is 4. So here we've done every combination of Cartesian product for this one. And we've done all the cardinalities. We've done a lot of work today. The the Cartesian product of sets does not need to be limited to 2 sets. We can do n sets, where n is an integer. And the way that we look at that is with this pi symbol. It's kind of like a multiplication. The Cartesian product of n sets is called an n-tuple. And we can use this symbol to extend this idea to more than just 2 sets. Once you get much beyond 2 or 3 sets, this is not something that you're going to want to do by hand. This is something that you would definitely use a program to do. All right, last example that we're going to look at in this section is example 10. Let A be the set of all A in the natural numbers such that A squared minus 1 is divisible by 4 and A is between 1 and 10. B is the set of x in Z, which are the integers, such that 3 times 3 cubed minus x squared minus 27x plus 9 is equal to 0. And I want to find B cross A. So in order to find B cross A, I need to find the elements of each set. In this last one, I just knew the elements, C, D, and F, and 3 and 9. But here, I don't really know the elements right now. I know I could find the elements, but I don't know what they are. So I need to do that first. So in A, I want to check the numbers 1 through 10 to see if that number squared minus 1 is divisible by 4. That's what this set is telling me to do, where A is a natural number between 1 and 10. So let's see. Let's check 1 first. So for 1, I am looking at 1 squared minus 1 is 0. Is 0 divisible by 4? Sure, 0. So that one's going to work. So 1 is going to be an element in this set. Let's look at 2. 2 squared minus 1 is 4 minus 1, which is 3. Is 3 divisible by 4? No, it's not. Let's look at 3. 3 squared minus 1 is 9 minus 1, which is 8. And that one is divisible by 4. So I'll keep going down the list here. 4 squared minus 1 is 15. That's not going to work. 5 squared minus 1 is 24. That does work. Let's see. 6 squared minus 1 is 35. That doesn't work. 7 squared minus 1 is 49, 48. That works. I'm noticing a pattern. Looks like all the odd ones are working and none of the even ones are. It's because I'm subtracting 1. 8 squared minus 1 is 63. That doesn't work. 9 squared minus 1 is 80. That does work. 10 squared minus 1 is 99. And that doesn't work. So, therefore, I'm going to use these 3 dots to represent therefore. We're going to talk about this more in the future. Therefore, A is the set 1, 3, 5, 7, and 9. So now I know the elements of A. So when I do B cross A, all of the second elements in that parentheses are going to be 1, 3, 5, 7, and 9. So now I'm ready to look at B. So B, I want to solve the equation. And then for my answer, I want to include only integers. So if there are any fractions, I don't want to include those. And I'm only including only integers because it's telling me that the x's are elements of the set Z, which are the integers. So that means no fractions. So here we go. 3x cubed minus x squared minus 27x plus 9 equals 0. This one I think I can factor by grouping. And factor out an x squared, and I get 3x minus 1. This side, I'm going to factor out a minus 9, and I'll get 3x minus 1. So my factors are 3x minus 1 and x squared minus 9. I'll do one more step here. 3x minus 1, I can factor x squared minus 9 is a difference of squares. X minus 3, x plus 3 equals 0. So that means x is 1/3, 3, or negative 3. And I just said I wanted only integers. So I'm not going to include that 1/3 because it's not an integer. So therefore, B is the set -3, +3. No 1/3. And now I think I'm finally ready to do B cross A. And that's going to be -3 and 3 cross 1, 3, 5, 7, and 9. So I'm going to have 2 times 5. I'm going to have 10 elements in this Cartesian product. So my elements are going to be -3, 1, -3, 3, -3, 5, -3, 7, and -3, 9. Then I'm going to have 3, 1, 3, 3, 3, 5, 3, 7, and 3, 9. That's my 10 elements. The cardinality of B cross A is 2 times 5, which is 10. Which, if I count my elements, I can see 10. Doing this cardinality check at the bottom is a great way to check to see, did I get every possible pair or did I miss one? Because there's supposed to be 10 and I can see that I got 10. Okay, that is the end of this section.